Okay, I'm gonna take you through just a little bit why in analysis of variance, why F is actually distributed like an F distribution. So let us, and that is for the ANOVA type analysis of variance. In general, such an F, if we go, I'll just discuss specifically the one-way ANOVA. We have seen that the F-statistic comes as the mean square for treatment divided by the mean squared error. That is the F-statistic, which measures how different the groups are versus the variability within groups. I want to start out saying, by always I mean, the mean squared error. This is really an estimate of the underlying variability. And I should emphasize that we would have a model like this, where the residuals, or the errors, follow a normal distribution with some variance sigma squared, the same for each group. The mean squared error coming out of the ANOVA table, the average variability within groups is, in a way, of course, the estimate of this average variability. And put differently, if we want, what would we expect from such a mean square? We would expect it to be, on average, the underlying within group variance. So the MSE, which is the denominator of the F-statistic, is always, in a way, an estimate of this within group variability. Now we should have a look at the numerator, and that is MSTR. So let us write it as this: the sum of the groups, the number of observations within each group, times the group average minus the overall average squared. So this is, this was the sum of squared, then we should actually divide by k minus 1 to have the mean squared for treatment. Now, I'm going to take you through the argument under an assumption. I'm going to assume, just for simplicity, I'm going to assume that all the NIs are the same. I mean, this is not an assumption as such for the whole ANOVA, one-way ANOVA setting. Also, it's not really an assumption for the interpretation I will give you. It's just easy to make it exact under this assumption. So I'm going to make this assumption, and then I can show you like this. If I should make it explicit, let me write it out again. It's just, of course, the same formula once again, where I've taken out the NI, which is now the same, so I take it outside the summation sign. Let me put it like this. Then I could also write list, if we look at this term here, and look at what that is. That is actually, if I write it in words, this is the variance of the group means, right? Look at this. I take each individual group mean, I subtract the overall mean, and I compute the sum of, sorry, it should not be n, it should be k here. I sum over the groups, and then I divide by number of group minus 1. Just the usual variance formula, right? So, mean square treatment, which is the numerator of the F-statistic, is really n times the variance of the group means. Now we should think about what is really the variance of the group means. Then we should say this is the usual. I mean, the claim, actually the thing that we want to prove is that this one follows an F distribution with k minus 1 times n minus k degrees of freedom, at least, and that is all we need, if the null hypothesis is true, right? That's an important little detail here. The null hypothesis is that all the groups are the same, right? Under the null hypothesis, this F-statistics follows an F. That is the theoretical important thing. So if we see something different from that, we reject the null. But the theoretical sampling distribution is to be specified under the null. This is the way it is always done in hypothesis testing. We express the sampling variability of the statistic under the null, assuming the null. So if we assume the null of all the groups being the same, then we should think about what is a variance of group means, really. Then we should think about a result that we learned back in chapter 6 and 7 already. What did we learn in chapter 6 and 7? Among other things, we learned that the variance of a random average is the variance of the original of the individual observation sigma squared divided by n, where n is the number that we use in the averaging, right? So repeatedly looking on averages and then computing the variance of such repeated averages, that would provide this expectation. Well, this means, in fact, that what we expect to be expressed in mean square treatment would be, as mean square treatment is n times the variance of group means, we would expect, I write the n again, and then the variance of group means. What do we expect when we have variance of group means? We expect this one. So altogether, I should emphasize under the null, otherwise this breaks down, meaning that under the null, the MS treatment should also, on average, express just the sigma squared, exactly as the denominator of the F. So both the numerator as the denominator under the null should be sigma squared. This is, in fact, like when we use the F for comparing two variances, this is in fact what proves, and this is as far as we'll take it here, that the expect of F under the null would then be around 1, and more specifically that the F statistics actually follows an F distribution with the relevant and correct degrees of freedom. So basically, if nothing is going on, the F should be around 1. If it becomes larger, it is a signal towards that the groups are really different, and the distribution to use as the measure is the proper F distribution that comes out as a consequence of this result. This is as far as I will take it here. Thank you.